When we consider the material that a wave propagates or travels through, we need to have some kind of model, and one of the models that we use that's very idealized is called the isotropic medium. And an isotropic medium just means that the density is consistent, or we can put it does not change at any point. Now, realistically, there are very few things that are completely isotropic. Probably the closest that we can come up with is a vacuum. It would probably be the closest isotropic medium. But we can also model things in air and also even the Earth. Even though it isn't perfectly the same density, for certain calculations and short distances, we can consider the Earth to be isotropic. Another idealized idea is a point source. These are not really real sources of waves. We normally don't think of a point source exactly, but it comes very close. And a point source is just a singularity from which waves propagate. Or travel, I guess is a better word. And because it's a point source, it's going to have spherical waves. Now, the best example that I can come up with for a point source is a light bulb. That's probably the closest example that I can come up with. So these isotropic mediums and point sources allow us to be able to find relationships with excuse me, with the intensities and amplitudes of our waves. So we defined intensity I as equal to our average power divided by the surface area. And for a sphere, you can look this up in your book, surface area is 4 pi r squared. So that's we just substitute that into our equation. And using this model, you can see the different wave fronts that are coming out. So say that the dark blue would be your peak or your crest, and the white would be your trough. You can see how they would radiate out from the center. Now let's define I1, our intensity 1, to be at the distance R1, and our intensity 2 at distance R2. So if we come up with a ratio, I2 to I1, that's just going to be the average power over 4 pi R2 squared over average power over 4 pi R1 squared. Now, I'm going to try to convince you that the average power is going to be the same no matter whether I'm at the intensity 1 at distance R1 or at intensity 2 at R2. So let's think about it in this way. Let's say that I have a certain light bulb at the center, and it has a certain amount of energy, and it's a 300-watt light bulb. So the energy per time, remember that average power is equal to energy divided by time, and there is no surface relationship here. There's no standard surface that is defining that. But now the intensity is based on the surface. So if I were to have a little differential area on this surface, this sphere that's defined by R1, and I integrate the amount of power, differential power, through all these little areas coming through the light energy, and I integrate all around that sphere, I would expect to come up with 300 watts, because all of the energy that's being sent from this source and the amount of power is going to be constant. It would have to be, because then if it wasn't, I'd be adding energy into the system that I can't account for. And if I were to take the differential area on the larger sphere, R2, and integrate all the little differential powers all the way around this sphere where you have R2, then also I should come up with 300 watts total. So the energy is being spread out over the surface of the spheres. And because it's being spread out over the surface, there is less energy per differential area that we're able to measure. But we always would get 300 watts because that is what our source is. So since the average power is equal, then those are going to cancel out. The 4 pi's are going to cancel out, and I'm going to come up with a ratio of R1 squared over R2 squared. Now, this makes sense based on this configuration, R1 less than R2, and we would anticipate that the intensity further away would be less than the intensity close in, and R1 squared divided by R2 squared is always going to be less than 1. So this makes sense, and it's the same thing as if you're standing right next to a 300-watt light bulb. It's very bright, very intense, but if you move away, the intensity goes away. Now, if you were to double your distance, again, you would find that the intensity would decrease by a factor of 4 because of that energy being spread out. Now, the area A2 over A1. I'm sorry, this is amplitude. This is amplitude. So amplitude A2 over A1 would equal R1 over R2, and the amplitude would be decreasing because we expect that as the wave travels through this medium, there's going to be a dispersion of energy, and so the amplitude is going to decrease as the energy gets spread around the sphere, and so the amount that the amplitude decreases is R1 over R2, and again this will always be less than 1 because R2 is greater than R1. So these are idealized. They're not real per se. Nothing is ever an isotropic medium and nothing is ever a point source. But it is useful in certain problems to be able to use an ideal method or an ideal properties to be able to come up with answers to questions.